I would like my student will be here, but he has obligation. He's a big sportsman and played basketball in Austria, and his obligation in the club doesn't allow to come here. I hope that I can present as he present this plan was, but it's like that. So this steel is usually used for ballistic protection. Generally has ultra high strength, high hardness, and good utility, and is used for production of tanks and armored vehicles. And what we expect as this from this steel on the field. So one thing is possibility to build the bullet, possibility to deform the bullet, and the third thing, if the bullet penetrates, then absorb the energy of the bullet. But usually we want all three possibility from the material, and also due to production, we also want to have good weldability, which is some future work which will be done later. So we asked producer to give us the material which was heat treated, because last heat treated this tempering temperature as high as possible, but get still be in this value what we promised, because this then enable us to do well joints, which is not so degraded in heat effective zone due to softening of material. So this is something what we plan in future. But first, what we want to present here is then producer did some charge of material. Here is chemical composition of this steel, and the plan is to confirm this data and also do some fracture mechanic tests. S&B specimen was done, and we tested this to see if has material good resistant to crack growth. So this is tensor test. On the right are specimen which we use for this. The thickness of material was 8 millimeters, and we can see that we are inside what producer promised. So the yield point was above 1,400. The strength, ultimate tensile strength, is about 1,600. But with this charge, we get good elongation, which is maybe 40% what we promised, and also contraction was quite good. This is due to last heat treatment of this steel. The next test we perform, this is just explanation of the test. So we use instrumental sharpening pendulum for evaluation, and we hope that this energy for initiation will be lower than energy for propagation, because for this task, energy for propagation is the energy which is used to stop the bullet. And after the test, we look the fracture surface and try to get percentage of ductile and brittle surface. So here are tests, some of these tests, and here we can see that energy for propagation is higher than energy of initiation. This is something we hope that we will get, and we get. Because the material was just 18 meter thick, this test was done on this geometry which is shown down there, 8 times 10, and we can see that energy for initiation is approximately little bit about 11, and energy for propagation is 13. And this is due to this last heat treatment which was done, and percentage of the ductile fracture was more than 32. We are satisfied with that, and then we measure the hardness, because here we hope that we will still remain in the limit what we want, and we measure with weakest hardness and calculated the linear hardness, and the producer of the steel said that need to be between 480 up to 520, and we are inside, and this is also good. And then fracture test was done. It's a standardized procedure. So pre-fatigue was done on Rummel machine. Then fracture mechanic test was done on Speedwelt, and again for the marking of the crack, also use again this Rummel machine. Another part was done in Professor Vuherer labs, where we have equipment with Aramis, which is some optical measuring system, and can visualize the thing. And first figure is just calibrating, then it's testing, and some details from the test. And here are results of this test. Here up is the chart of applied force and COD, and down there is we use standardized normalized method according to ISM 1820 standard, and here is a resistance curve of this steel. And we are satisfied, and we are then proceed for of welding. So here are detailed results. So up is visualizing of the plastic zone with Aramis optic system at the crack tip, and here are results. So yes. We are also satisfied with this result, because the KG1 C was more than 25, and we hope that we will obtain more than 85, and we are satisfied. And next step will be welding. So here we stop now, and we are testing of this steel. We are satisfied with the results we get on tensile test. Also, impact Sharpie test, instrumented Sharpie test, also show that we have higher energy for propagation than energy for initiation. Also, this is good for this type of instruction. And at the end, we can see that our KG1 factor is more than 96, and we hope to get 85. But now will be degradation next stage of this study, because weld joints will be done, and then we will have lowering of the properties in heat effective zone, and also in weld zone we will not achieve such good results, and we will see what will be in future. This is
okay. Thank you.